Welcome to The Explainer. So, I'm genuinely super excited you're here today, because we are taking on what I can only describe as a truly high-stakes culinary mission. Based on our source material, we're going to break down exactly how to execute a structurally sound, perfectly deep-fried Twinkie right in your own kitchen, and more importantly, how to do it without causing a catastrophic hot oil disaster. Now, you might think making a classic State Fair staple is, pretty simple, right? Well, actually, as I was pretty surprised to learn, it's basically a marvel of structural engineering and physics.
To successfully pull off this high-calorie novelty, the source outlines a pretty rigid 6-step protocol for us. We'll be hitting 1. The thermodynamic vulnerability, 2. Protocol alpha, cryogenic stabilization, 3. Protocol beta, carbohydrate matrix, 4. Protocol gamma, thermodynamic application, 5. Extraction and sucrose dust, and finally, 6. A red team counter-analysis.
Okay, let's dive right into Section 1, the thermodynamic vulnerability, or assessing the initial threat.
Before we even get into the actual process, I really want you to think about this critical question posed by the text. What actually happens when you try to fry a standard room-temperature Twinkie? Like, why can't we simply unwrap the pastry, toss it straight into a pot of hot oil, and just hope for the best?
Well, the answer? Total catastrophic failure. Without the proper prep, you're going to run headfirst into a brutal thermodynamic reality. You see, the Twinkie's commercially engineered lipid-based cream filling just absolutely cannot handle that kind of heat. If it goes in unprotected, that filling rapidly liquefies, it boils almost instantly in the hot oil, and it literally violently breaches the surrounding sponge cake. It is a complete structural blowout. Reading about it really hits home exactly why these precise steps we're going to cover are so absolutely crucial.
Which brings us to Section 2, Protocol Alpha, Cryogenic Stabilization, Securing Structural Integrity.
So it turns out cryogenic stabilization is really just a highly technical way of saying you gotta freeze the Twinkie completely solid. Think about it. A room temperature Twinkie is basically just a highly aerated sponge. It completely lacks the structural integrity needed to hold onto a heavy wet batter. By freezing it, we're preparing that mass for extreme heat and making sure those internal lipids don't boil prematurely. It's actually kind of fascinating how such a straightforward, simple step solves such a massive physical threat.
The physical mechanics of this Protocol Alpha laid out in the text are beautifully simple. First, just unwrap 4 to 6 Twinkies. Second, and the source points out this is a really vital engineering detail, you want to carefully insert a wooden popsicle stick or a thick bamboo skewer roughly 3/4 of the way into the longitudinal center of each pastry. And then finally, just pop them onto a parchment-lined baking sheet to freeze. Now, the absolute crucial factor here is the timing. 2 hours is the bare minimum these guys need to spend in the freezer, though going overnight is definitely considered optimal by the experts. The text warns us that if they are even slightly soft, that wooden stick is going to rip right out under the extreme pulling weight of the wet batter we're about to mix up. So honestly, patience here is paramount. Don't rush it.
All right, moving on to Section 3, Protocol Beta, Carbohydrate Matrix. Time to engineer the batter. Taking a look at the precise chemical breakdown required to create this viscous emulsion, we start by combining our dry components. That's flour, sugar, salt, and, this is key, specifically 1 teaspoon of double-acting baking powder, which is absolutely essential for creating that CO2 lift inside the fryer. Then, in a separate vessel, we whisk our wet components, milk, an egg, and a tablespoon of neutral oil, which actively aids in the lipid crisping process. Mix the wet and dry until fully integrated. When you look at it, it's really just a specialized, high-performance funnel cake batter.
But hold on, you can't just use it right away. The protocol strictly demands letting this viscous emulsion rest for exactly 10 minutes to properly hydrate the starches. The source issues a pretty severe warning here. If you skip this resting phase, your batter is either going to be too thin and just run completely off your frozen sponge, or it'll be way too thick, leaving you with a disagreeably doughy crust instead of that perfect crisp shell we're looking for.
Let's hit Section 4, Protocol Gamma, Thermodynamic Application, also known as the fry.
Precision is literally everything at this stage. The instructions call for a deep Dutch oven or a countertop fryer filled with 3 inches of a high smoke point oil, something like peanut or canola. And that oil has to be brought to exactly 375 degrees Fahrenheit, monitored constantly by a calibrated deep fry thermometer. If it's too hot, the exterior burns before the inside can even thaw. If it's too cold,
The batter just absorbs the oil and turns into a gross, greasy mess.
Okay, here is your exact operational flow for submersion. You're going to hold the frozen Twinkie by the stick and submerge it entirely into the batter. Lift it out and allow the excess to drip off for exactly 3 seconds. Finally, carefully, and I mean carefully, lower the battered mass into the hot oil. The text makes a massive point to emphasize this. Do not just drop it in. I mean, unless you actually want 375-degree oil violently splashing back at you.
Once it's in the oil, something kind of magical happens. During that quick 3 to 4 minute fry window, as you're gently rotating the Twinkie with metal tongs, you create what's called the thermal differential. The extreme external heat rapidly creates this shatterproof, beautiful golden brown Maillard outer shell. And that shell acts like a thermal shield, right? It allows the completely frozen interior to safely thaw into a warm, molten state without ever actually reaching its boiling point. It is seriously just a perfect thermodynamic dance.
Moving to Section 5, Extraction and Sucrose Dust, Securing the Payload.
So apparently, tons of amateur engineers end up ruining their entire project right at the finish line. The protocol explicitly states, do not place your successfully fried Twinkie directly onto paper towels. If you do this, the trapped steam escaping from the bottom is going to instantly turn that beautiful, perfectly crisp crust you just engineered into a soggy, unappetizing paste. A wire cooling rack is absolutely required here to preserve the structural integrity.
To finish out the primary mission, the Twinkie must be dusted aggressively with powdered sugar, or sucrose, while it's still hot. The actual physics of sucrose adhesion requires that residual surface heat so the sugar properly sticks to the crust. Once dusted, the operation is complete. You want to serve it immediately while that thermal differential we talked about is still perfectly balanced.
But wait, we have Section 6, Red Team Counter-Analysis, the Mechanical Anchor Failure.
Just when success seems completely guaranteed, the source material throws in this fascinating red team analysis. And here is the absolute core of the issue, the mechanical anchor failure. As the source bluntly states, because the Twinkie is mostly air, the stick has very little actual mass to grip. Remember guys, this is a highly aerated sponge cake. If your batter is even slightly too thick, its heavy viscosity will literally pull the Twinkie right off the popsicle stick as you try to lift it out of the batter bowl. This critical vulnerability really forces us to weigh two competing philosophies against each other. Do you rely on the sort of aesthetic-driven amateur stick method, or do you pivot to the sheer mechanical efficiency of the professional tong method? Let's break down the bias inherent in the recipe. The stick method heavily prioritizes the classic visual aesthetic, the pure nostalgia of eating state fair food off a wooden stick. But it comes with a super high risk of tearing. Professional state fair vendors, they know this, so they entirely bypass the mechanical anchor failure. Instead of messing with a stick, they just use a long set of metal tongs to physically hold the frozen Twinkie right in the batter, and then they use those exact same tongs to gently drop it into the oil. Honestly, it is just mechanically superior in every way.
So, having seen the thermodynamic science, the cryogenic stabilization, and the red team analysis, I leave you with this final thought. When you step into your kitchen to execute this high-calorie marvel, are you going to risk the mechanical anchor failure just for that classic state fair aesthetic? Or will you put ego aside and engineer a truly foolproof fry using the professional tong method? The physics are in your hands now. Thanks so much for joining me on this explainer, and hey, happy frying!